If you're anything like me, then when you wake up in the morning, you're usually not refreshed and ready to go right back to bed. But what if you can wake up at the perfect time, energized and refreshed, ready to take on the day's challenges? That is what me and my friend Thomas have endeavored to do through our Base Off project, where we are trying to determine the optimal wake-up time using RMSSD data that will be personalized to you. We are in grade 9 and from King's Christian Collegiate, and we hope we are finding you dredgers well. Sleep is a bodily function for recharging and healing. It refreshes both the brain and body. Without enough sleep, it is impossible for a person to function. However, it's not just the quantity of sleep that matters for good sleep, and therefore a refreshed awakening. It's also the quality of sleep that matters. In order to wake up feeling refreshed, you have to sleep enough time and also wake up at a good time. Why? Because when sleep occurs, the body experiences sleep cycles. In some parts of the cycle, the body is in deep sleep. In other parts, the body is in light sleep. If I were to say wake up in a deep sleep, I would feel tired because my sleep wasn't really complete. In contrast, if I were to wake up in light sleep, I would feel much more refreshed, even if I woke up 15 minutes earlier than I had if I had woken up in deep sleep. The solution to this is to wake up in a light sleep. When an individual wakes up in a light sleep, they feel much more refreshed since their mind is already active. In order to wake up in a light sleep, Thomas and I decided that an algorithm to determine which sleep stage our user is should be used. Of course, the question now is, what stage should we wake up our users? The best stage to wake them up in is stage 1, where their brain activity is much higher and they are much readier to wake up into the real world. As for how would we determine what sleep stage they are in, we'd use RMSSD data, the root mean square of successive differences between normal heart rates. This is some metric under heart rate variability, or HRV, and deals with basically separating how much your heart rate is changing into an easier to measure data point. The hypothesis for our project was that using input from a subject's RMSSD, it is possible to accurately predict the optimal wake-up time of said subject. Because of the nature of our project, there were no physical materials used. However, there were some digital resources such as Donnie, Python, and also multiple Python libraries such as matplotlib.pyplot, datetime, and pytest, which we use extensively in our code. Donnie was especially used as an integrated development environment that helped us parse and save all our data files. Matplotlib.pyplot is a Python library that we used to plot graphs. Datetime was what we used to help us keep track of time, date, in chronological order. And pytest is what we used to help us test our algorithm.
The algorithm was written over a long period of time. First, the data was extracted from the Fitbit. Once the data was obtained, it was sorted through and all the heart rate variability details for each night were saved to a separate folder as the data. Then a parsing code was written to sort through the data, and the timestamps in RMSSD data were saved to .text files. Then the actual algorithm was written. This is how it worked. Before anything, the person would set an alarm time for when the absolute latest time was they could wake up at. Then the algorithm would keep track of the days using date time. Then it would go through each night, looking at the data 2 weeks prior to that date. Using the data from the past 2 weeks, it calculates the threshold from the median of all the RMSSD data. In the current night, it starts calculating 30 minutes before the alarm time. If it sees an RMSSD lower than the calculated threshold, it will wake the person up, as low RMSSD signifies light sleep. If it does not see any RMSSD lower than the threshold, it will wake the person up at the alarm time. In that unfortunate event, the person will probably not experience a good, refreshing awakening. The results of the algorithm were surprising. They showed that the RMSSD fluctuates during the night. They also showed that when entering into sleep, the RMSSD was relatively high compared to the rest of the sleep. It showed that the average RMSSD was about 40 RMSSD. The exit point of the sleep was also about 40 RMSSD. The exit point was usually below the previous point on the graph. This is strange because it means that the highest points on average were the entrance and exit points of the sleep. Because if the entrance point was above average and the exit point was average, something has to compensate for the entrance. However, this does not mean that the RMSSD was all low in the middle. On the contrary, it fluctuated from as high as 80 RMSSD to as low as 30 RMSSD. The RMSSD tended to stay around the 30 RMSSD to 40 RMSSD mark. These are all generalizations, however. There were almost no nights which followed all of these observations.
Using the data acquired, it is affirmed that it is possible to predict the optimal wake-up time for a specific person. As mentioned previously, the hypothesis was that using input from a subject's RMSSD, it is possible to accurately predict the optimal wake-up time of said subject. We have been able to use input from our own RMSSD data and have been able to predict optimal wake-up times of previous nights. Some of our next steps include building a physical wearable, or prototype. That way we can collect our own RMSSD data rather than relying on Fitbit to collect it for us. Our wearable would be able to measure heart rate, transform that into RMSSD, and then send that to Raspberry Pi, where more complex coding and algorithms could be stored. Additionally, this could connect to LED lights, which could be used to actually wake people up at the optimal time in real time, as opposed to just in a simulation. More research can also be done on machine learning and pattern recognition, using something such as TensorFlow. This will allow us to have higher, deeper level connections between RMSSD and sleep cycles. And it could also allow us to incorporate other sensors, such as breathing, oxygen, and even movement into our algorithm. Another potential next step is more research into using the data in an HTML website where our users could actually view the graphs of data made automatically for them, similar to what we have now, but projected to be easier to use. Image credit goes to flaticon.com, Wikipedia, VectorStock, Fitbit, PellSensor.com, the Artisan Dictionary, and Dana blog. Thank you so much.